Hello students, welcome to EPG Pathshala. I am Dr. Savita Sharma from University of Delhi and today we are going to talk on module Ferroelectric Photovoltaics Solar Cell Part 2 under the paper Thin Film Science and Technology. So students, let us see what we are going to learn in this module. First of all, we are going to learn about the conventional solar cells and their mechanism. Secondly, we will learn about the mechanism of ferroelectric photovoltaics. Then next, we are going to compare the conventional photovoltaics with the ferroelectric photovoltaics. Number 4, we are going to learn about the history and current status of ferroelectricity and the ferroelectric photovoltaics. Then next, we will study about the advantages and disadvantages of the ferroelectric photovoltaics. So before going into the detail, let's have a brief introduction. As we all know, researchers worldwide are working very hard to open different corridors for the production of renewable energy to meet the evolving demands of the inexhaustible energy and clean fuel sources. Harnessing solar energy as an alternative to compensate the depleting non-renewable energy resources is a technological field with great potential. Photovoltaic materials and devices, commonly known as solar cells, convert sunlight into electrical energy. Generation of electricity in a clean, quiet and reliable way is one of the major attractions of photovoltaic technology. On illumination of a conventional semiconductor-based photovoltaic cell, generation of charge carriers, that is the electron-hole pairs, take place at the depletion region, that is at the p-n junction of the semiconductor. The carriers thus produced are responsible for the generation of photocurrent, which can be harvested in a useful manner. The electronic band gap of the semiconductor determines the photovoltage produced by the photovoltaic cell. So first of all, let's discuss about the conventional solar cells. The photovoltaic technologies can be classified on the basis of the material used, which in turn is responsible for the determination of the current voltage characteristics and the efficiency of photovoltaic device. High conversion efficiencies have been demonstrated by photovoltaic cells based on silicon and 3,5 semiconductor compounds. The high conversion efficiencies are shown by single and multi-junction derivatives of these materials and find applications in space and terrestrial technologies. Inorganic, organic and quantum dot cells are some emerging photovoltaic cell technologies. Though the efficiencies of ferroelectric photovoltaic cells are lower as compared to their semiconductor counterparts, but they have found place in figure 1 due to their cost effectiveness. Here the given figure shows the review chart showing the work done on solar cells. It shows the review of various companies, universities and research institutes behind the advancements of solar cells based on silicon. It's impressive to see how National Renewable Energy Limited, which is NREL, has been heavily involved in many technological advancements since over the 90s. Other heavyweights have been research labs like Fraunhofer and Spectrolab. Focusing on the corporate giants, we notice that Sharp but also Panasonic, Sanyo and Siemens have contributed to the field with their own R&D departments. This we can see in the above given figure, figure 1. There is an ongoing pursuit for further improvement of the photovoltaic cell efficiency along with reduction in the fabrication cost. The photovoltaic industry and research is driven by the quest of maximizing the power generated per rupee. The past decade has seen the momentum in exploring the viability of alternate materials to increase the efficiency of photovoltaic cells. Lately, ferroelectric materials have been used for photovoltaic technology, and this research area is generally referred to as ferroelectric photovoltaic. So now let us discuss the mechanism of the conventional p-n junction based solar cell. Silicon based photovoltaic technology has dominated the solar cell industry over the past many years and continues to foster till date. Typically, photovoltaic effect involves two processes. Number 1, creation of electron hole pairs as the electrical charge carriers and formation of electric current due to the motion of separated electrons and holes. In the junction-based photovoltaic effect, the internal electric field only exists in a very thin space charge region of a p-n junction or Schottky barrier, which separates the charge carrier as shown in the figure 2. Without the internal field in the bulk material region, the photo-generated charge carriers swept out of the depletion region have to diffuse to the cathode or anode. Thus, the charge transportation is often limited by diffusion in the junction-based photovoltaics. The open circuit photovoltage or VOC cannot exceed the energy barrier height of the junction, which is usually lower than 1 volt for silicon. Moreover, a p-n junction is not a prerequisite for the photovoltaic effect. The photovoltaic effect can originate from a variety of other mechanisms such as gradient in a chemical potential or spin polarization. So in the following given figure, figure 2, band diagram of conventional p-n junction is given, which showing the conduction band, the valence band, the band gap and the open circuit voltage VOC. Here h nu is the incident photon energy and E is the elementary electric charge. So let us now discuss the mechanism of ferroelectric photovoltaics. Another mechanism which was discovered in non-centrosymmetric materials such as ferroelectrics and is called the bulk photovoltaic effect. This differs from the conventional junction-based interfacial photovoltaic effect in semiconductors such as p-n junction or Schottky junction. Ferroelectrics have shown potential as promising material for future photovoltaic applications. Observance of high open circuit voltages in ferroelectric thin films have generated considerable interest in the field of ferroelectric photovoltaics in recent years. The field of ferroelectric photovoltaic is evolving and not yet completely understood compared to the semiconductor-based photovoltaic technology. Bulk ferroelectric photovoltaic effect is a fascinating phenomena with many unique features such as extremely large photovoltage, where a photocurrent is proportional to the polarization magnitude, and charge carrier separation in homogeneous media. In bulk photovoltaic effect, the remnant polarization and the polarization induced internal electric field exist over the whole bulk region of the ferroelectric, rather than a thin interfacial depletion layer in case of the semiconductors. In case of bulk ferroelectric photovoltaic effect, the charge transportation is not limited by diffusion, and VOC, which is the open circuit voltage, is not restricted to the energy barrier or the energy band gap of the material. As a result, the photovoltage observed here is significantly higher than the electronic band gap and proportional to the interelectrode distance in the polarization direction, which is found to be originated from the engineered domain walls of the ferroelectric material. Ferroelectric photovoltaic effect was originally investigated in several ferroelectric perovskite oxides such as barium titanate, lead titanate, lead zirconium titanate, lanthanum doped lead zirconium titanate, and lithium niobate. Oxide materials are cheap, abundant, stable, highly light absorbing, and their properties such as band gap and conductivity can be systematically tuned through chemical substitutions, making them promising candidate for thin film ferroelectric photovoltaics. Much excitement was generated due to the large open circuit photovoltage. In some case, open circuit photovoltage even exceeds 102 volts, which is produced when crystal was subjected to illumination. However, the light to electricity conversion efficiency, which is also called as power conversion efficiency of the bulk photovoltaic effect in ferroelectric thin film based solar cell is reported to be significantly lower, that is less than 10 raised to the power minus 4, than that of commercially available silicon based solar cell. One major obstacle in achieving high conversion efficiency is the intrinsically low bulk conductivity of ferroelectric domains. Indeed, any effort to increase the bulk conductivity of ferroelectric domains has proved to be ineffective because leaky domains cannot withstand strong electric polarization, as charge density associated across the domain wall will therefore be reduced for a leaky ferroelectric material, which results in a low open circuit voltage. Moreover, the large energy band gap of ferroelectric materials allows strong absorption of light in ultraviolet region only. A simple possible explanation of ferroelectric photovoltaic or FEPV is schematically illustrated in the given figure 2. When a light source of wavelength corresponding to the energy band gap of the ferroelectric material is incident, photons are absorbed with the generation of charge carriers, which are electrons and holes. The photogenerated electrons and holes are driven by the polarization induced internal electric field in opposite directions and thus contribute to the photovoltaic output. In other words, this effect is associated with the loss of inversion symmetry in the distribution of defects, impurities, space charges, and polarizations in ferroelectric materials. So in the given figure, you can see the schematic illustration of mechanism of photovoltaic effect in ferroelectric thin film. In the part A of the figure, you can see the two electrodes, the bottom electrode being platinum and the top electrode being gold. And between these two electrodes, there is a ferroelectric material. The field or the voltage is applied with the help of these top and bottom electrodes, and we can see that after the application of voltage, the charges, that is the electrons and holes, get separated and they start moving towards the two electrodes, and their movement in the opposite directions contribute to the photovoltaic output. So the photogenerated electrons and holes are actually driven by the polarization induced internal electric field. In the second part of the figure, you can see the other side, that is between the top and the bottom electrodes, there is a ferroelectric layer. In this case, the example of ferroelectric layer is the BTO and BFO, that is bismuth ferrite and barium titanate multilayer thin film, in which we can see that after the light is induced on the sample, the domains are aligned, and within that dipoles, the electric dipoles, the charges are separated. These charges are actually the carriers, which are the electrons and holes which move later on towards the opposite direction, giving the polarization. The output signal of solar cell made up of ferroelectric material can be tuned by various other means, including mechanical, electrical and magnetic functionality. Designing of materials having enhanced magnetoelectric properties can be achieved using the principle of strain engineering employed to multilayer structures and superlattices. In this regard, recent study of a number of multilayer heterostructures containing alternating ferroelectric and multiferroic layers such as lead zirconium titanate and cobalt ferrite, barium titanate and bismuth ferrite, bismuth niobium ferrite and barium strontium titanate, etc. has been useful in observing the enhanced magnetoelectric properties. So let us now compare the conventional p-n junction based photovoltaics with the ferroelectric photovoltaics. Charge carriers, that is the electron hole pairs, are generated when a ferroelectric material is illuminated with a light of wavelength corresponding to its energy band gap. A photovoltaic output is generated when the photogenerated carriers are separated and driven to the electrodes by the polarization induced by the internal electric field. This schematic of photovoltaic mechanism, that is the semiconductor p-n junction and the ferroelectric thin film, are illustrated in figure 3. On the other hand, for a junction based semiconductor photovoltaic device, the charge carriers are separated by the electric field which exists in the depletion layer at the p-n junction interface. Thus, in ferroelectrics, the photovoltaic effect is a bulk-based effect, which is different from the junction-based semiconductor photovoltaic effect. In ferroelectric photovoltaic, the photovoltaic responses can be generated without forming complex p-n junction structures, since the internal electric field is not limited to the interfacial region. Simple schematic of this mechanism in conventional p-n junction and ferroelectrics is shown in figure 3 in the part A and the part B. Now, after studying the mechanism of the ferroelectric photovoltaics, let us see the current status of the ferroelectric photovoltaic effect, and the history from where it is coming. The photovoltaic effect in ferroelectric ceramics, that is in the bulk, and the single crystals such as barium titanate, lead zirconium titanate, and lithium niobate were observed earlier. The non-centrosymmetric nature of the unit cell gives rise to this effect. However, owing to a small current densities of the order of nanoamperes per centimeter square due to large band gaps in the ferroelectric materials, the photovoltaic efficiency was limited. The observation of photovoltage larger than the band gap in thin films of bismuth ferrite lead to the renaissance of research in photovoltaic ferroelectric materials. So an open circuit voltage of about 20 volts was reported for bismuth ferrite thin film, which have a band gap of 2.67 electron volts. It was further shown that the photovoltage could be enhanced or reversed by controlling the ferroelectric polarization, which is in turn controlled by electrical poling in lead-based thin films. Now, poling is a process of applying an electric voltage higher than the coercive field to a ferroelectric material while cooling it from transition temperature to room temperature. Poling results in orienting the ferroelectric domains in one particular direction, leading to maximum polarization. The internal polarization, or PS, is not uniform throughout the ferroelectric. For instance, at the surfaces, the crystal terminates and polarization becomes zero, and in the neighborhood of defects, the polarization of internal or the value of the internal polarization may differ from that of the perfect crystal. This variation in internal polarization gives rise to depolarizing field. This field can be compensated by the flow of free charge in the crystal or by the free charge in the surrounding medium at the crystal surface. The depolarization field energy, which is also represented by WE, is zero for a totally compensated crystal in equilibrium. However, for insulators, this is not readily attained. Ferroelectric materials, which exhibit strong bulk photovoltaic effect, have been widely explored since 1956 for harvesting light energy. Compared to other ferroelectric materials like barium titanate, lithium niobate, lead titanate, lead lanthanum zirconium titanate, with a wide energy band gap, the smaller band gap of bismuth ferrite can generate a significant current in response to the interaction with visible light photons coming from sun, which acts as an abundant renewable clean energy. The above mentioned discussion clearly point towards the advantages of ferroelectric materials, which crystallizes in the perovskite structure and are compatible with many other functional compounds, such that their ferroic property and electric behavior can be tailored for the desired photovoltaic applications. So now let us discuss the advantages of ferroelectric photovoltaic effect. First of all, in ferroelectric photovoltaic, the photovoltaic responses can be generated without forming complex p-njunction structures, since the internal electric field is not limited to an interfacial region. Secondly, extremely large photovoltaic voltage. Photovoltaic voltage, which is represented by VOC, in this case is not restricted to the energy barrier or the energy band gap of the material. As a result, the photovoltage observed here is significantly higher than the electronic band gap. Third, the output signal of solar cell made up of ferroelectric material can be tuned by various other means including mechanical, electrical, and magnetic functionality. Then next, oxide materials are cheap, abundant, stable, highly light absorbing, and their properties such as band gap and conductivity can be systematically tuned through chemical substitutions, making them promising candidate for thin film ferroelectric photovoltaics. The photovoltaic can be enhanced or reversed by controlling the ferroelectric polarization, which in turn is controlled by electrical polling in lead-based thin films. Then the sixth advantage is ferroelectric materials are compatible with many other functional compounds such that their ferroic property and electric behavior can be tailored easily for the desired photovoltaic application. Then the seventh advantage is by using suitable ferromagnetic electrodes and a clever design of the device structure, it may also be possible to control the spin polarization of the output photocurrent, favoring device miniaturization with novel applications such as optical microsensing, light-controlled elastic micromotion, and microactuation in micro-electromechanical systems. Then lastly, exploitation of suitable ferroelectric materials having narrow band gap useful for visible region are promising for their potential application in both the novel optoelectronic and the solar energy devices, making them multifunctional. Now, along with the so many advantages of the ferroelectric photovoltaics, there are certain disadvantages of this effect as well. So let's discuss them. The number one disadvantage is that the use of ferroelectric thin films for photovoltaic applications, the limitation here is the leakage current that degrades its multiferroic and hence photovoltaic properties. Secondly, major obstacle in achieving high conversion efficiency in ferroelectric photovoltaics is the intrinsically low bulk conductivity of ferroelectric domains. Thirdly, the large energy band gap of ferroelectric materials allows strong absorption of light in ultraviolet region only. And then lastly, the internal polarization is not uniform throughout the ferroelectric material. And this variation in internal polarization give rise to depolarizing field. So students, let us now summarize what we have learned in this module. First of all, we studied about the conventional solar cells and the mechanism of a conventional semiconductor-based solar cell. Then secondly, we learned about the mechanism of the ferroelectric photovoltaics. Then next we compared the conventional semiconductor p-n junction based photovoltaics with the ferroelectric photovoltaics. Then next we saw the history and the current status of the ferroelectricity and ferroelectric photovoltaics. And then we saw the advantages and disadvantages of ferroelectric photovoltaics. Thank you.